Hello again, AP Physics students. In today's lesson, we are once again going to continue to look at the electric field due to objects that have a continuous charge distribution, specifically in scenarios where, again, we just can't really apply Gauss's law. And this time around, we're going to look at a thin ring of charge. So if we look at the picture in the bottom left-hand corner, we have a ring that has a radius of capital R. It has a positive uniform linear charge density, which we'll write down as positive lambda. The ring is centered at the origin, and it lies in the xy plane. And what we want to do is we want to figure out the electric field at a point P that is located a distance z from the center of the ring along the x-axis. Now, in comparison to the previous two lessons, so the first one we had a finite uh, length of charge, and in the second one we had an arc of charge. Those were problems that we could deal with in two dimensions. This one's going to be a bit weird with some of the geometry just because the way in which we have the picture drawn is in three dimensions, but overall nothing too difficult in comparison to the previous ones, just because the ring does have some pretty nice symmetry to it. Okay, so let's go through the series of steps in terms of like how we can figure out what the electric field is at point P. Again, you're going to find that the steps are going to be quite similar compared to the lessons 1 and 2 for this unit. And it's going to be the same idea like every time that you're trying to like figure out the electric field due to a continuous charge distribution. So the first step is you want to figure out using symmetrical arguments, what's the direction of the electric field at point P. Now, that's actually pretty simple to do. So I'll just draw like a couple of charges that are on this ring here. So let's say we have a charge that's somewhere along the positive x-axis. Now, that charge, if you put a positive test charge at point P, would cause the electric field to kind of be like in a direction, maybe something like this. If you put, if you look at a charge on the opposite side, that would cause the electric field at point P to point in a direction that looks like that. So if we look at these two vectors here, these vectors would be along the xz plane. So what would happen with these two ones is that the x components would cancel off, and you would just be left with the net direction of the electric field pointing in the positive z direction. Now, I'll erase those two, and then just kind of show you what happens if we look at some charges at a different point. So let's get rid of that, get rid of that. Okay, get rid of this, get rid of this. And then let's say that we now have, we look at a charge up here and a charge down there. So if we identify the direction of the electric field due to this charge at point P, it'd be something like down and towards the right. And if we look at the direction of the electric field due to this charge at point P, it'd be something that's up and towards the right. So these two vectors would be lined up in the YZ plane. And again, you can see the components, the Y components would just cancel off. So again, you just have the net direction of the electric field pointing in the positive Z direction. And it doesn't matter where you do this along the ring. I picked these points because they're the easiest to deal with because the electric field vectors would lie in a specific plane. But nonetheless, no matter what, all of the components are going to cancel off, leaving you only with a Z component that points in the positive direction. So at point P, all of your X and Y contributions are going to cancel off, which means that the net direction of the electric field at point P is going to be directed towards the right along the Z axis. And that's because the ring of charge is positive. So my electric field vector just points towards the right. That's my direction. That's easy to identify. The magnitude, that's going to be a bit more of a complicated process to figure out what that equation is going to look like. Step 2, we're going to take this ring. Now, this ring has a circumference that I'm going to identify with capital C. And we'll say that the entire ring contains a total charge of capital Q. We're going to take this entire ring and we're going to break it into a bunch of little tiny chunks. Now, each little chunk, because we're looking at a curved portion of the total circumference, we're going to represent each chunk with an incrementally small arc length that we're going to represent with delta S. And each differential arc length is going to have a differential charge to it, which is going to be delta Q. So we represent this on the picture. I have my differential arc length element, which just means a very small chunk of the ring, very, very tiny chunk of the ring. And it has an arc length that is delta S, and it has a charge delta Q that is contained within it. So again, just one small chunk of the entire circumference. We then want to write an expression for delta Q in terms of delta S, and then we'll write it in the calculus notation. We'll drop the deltas and write it in terms of dQ. So if you set up a ratio again, if you take the total charge in the ring and divide by the charge in that differential element, that would be equivalent to taking the entire circumference of the ring and dividing by the arc length of that really, really tiny chunk. If we take that equation and manipulate for delta Q, we then have delta Q is equal to Q over the circumference times delta S. But if you take the total charge and you divide by the total circumference, that is your linear charge density. Again, linear charge density, because if you think of the ring as being, I don't know, like I know the ring is rigid, but if it was like a ring that was a string, you could cut the string and you could just like unfold it into a straight line. So in essence, like it is just a line, but just bent into the shape of a circle. So therefore, we can just represent the total charge divided by the circumference as the linear charge density, which then tells me that the amount of charge contained in that differential element is equal to the linear charge density multiplied by the arc length of that differential element. And turning it into the calculus notation, we would then have dQ is equal to lambda times ds. Step 4, we want to identify what the distance is from point P to the location of the differential element. Now, here's where it gets a bit weird because now we have to like deal with a picture that's going to be in 3 dimensions. So if we represent this distance on this diagram, the distance r would be just, you can just draw it from point P going to the position of my differential charge element, which is located somewhere right here. So it's somewhere between this positive y-axis and this x-axis right here. Now, to help identify the geometry, there's 2 ways you can do this. So we can look at this in 3 dimensions, or we can look at it in terms of like a top view perspective of what this ring would look like. Now, if I look at it in terms of 3 dimensions, I'm also going to draw a line that connects the origin to the position of where the differential element is. So if I do that, and I'll do it in a color purple here. Okay, so let's go from the center of the center of the ring, and let's draw a line that kind of just does that. That looks pretty bad. Let's just erase that because the line's not actually matching up with where I want it to go. Okay, let's see if I can do a slightly better job. Okay, something like this. Okay, now I'm going to shade in. This forms a triangle. Now, I'll shade the triangle in to make it a bit more clear in terms of the triangle we're looking at. So, shade this triangle in. Now, this triangle is not perfectly oriented in the YZ plane. Think of it as like being oriented in the YZ plane, but then it's tilted a bit into the page in the direction of this x-axis. So if you look at the actual diagram here, we want to try to identify what the right angle is. And what the right angle would be is the right angle is actually this angle down here, okay? It's just hard to identify because the picture is drawn in 3 dimensions. Now, In terms of what this side of the triangle is, well, the distance from the center of the ring to the differential element, well, that's just the distance from the center of the ring to the outside. That's the radius. So that's capital R. So we have a right angle triangle where the two legs of the triangle are the radius and this distance z, and the hypotenuse is going to be lowercase r. Now, if you find it difficult to visualize like that, we can also look at this from a top view perspective. So from a top view perspective, again, we have my x-axis drawn horizontally, and we have my z-axis like this. Your y-axis would be coming into and out of the page. We have point P here. Okay, so your ring lines up with the x-axis. And we'll draw my differential charge element a little bit towards the right of the y-axis, so in the direction of the x-axis right here. So if we draw a right angle triangle, okay, so again, the distance from P to the position of the origin, that would be Z. The distance from P to the differential charge element, that's R. And then this missing distance right here, as identified on the picture from a top view perspective, that actually is the radius of the ring. Now we have a right angle triangle, and I can use that right angle triangle to write an equation for what r is. Now, we'll also get an equation for r squared. We use Pythagorean theorem to do that. So we'd have little r squared is equal to z squared plus capital R squared. And if we want an equation for little r, we just take the square root of both sides. So that would then just be r is equal to the square root of z squared plus capital R squared. We'll make use of both those equations in just a moment. Now, step 5 is we want to identify what is an equation for the electric field at point P due to this single differential charge element. We're going to call that dE. So if we have a positive differential charge element located in this red section up here, then a positive test charge wants to repel away from that. So that's going to be a vector that, from our perspective right here, points kind of like in the direction that's down and towards the right. Now, again, just be aware that would actually be a vector that is pointing in 3 dimensions. It would have both an x, z, and it would have a y component to it. So again, to kind of look at this, we'll eventually need to look at a top view perspective to make sense of the geometry, but we don't need to get to that yet. So once again, going back to the equation for the electric field due to a point or a source charge, the electric field magnitude is equal to K, Coulomb's constant, times the charge divided by little r squared. We're going to turn that into the electric field due to a differential charge element. So that would be dE is equal to K times dQ over little r squared. But from the previous page, we identified that little r squared is equal to z squared plus capital R squared. And dQ from, I think the slide before that, dQ is equal to lambda times ds. So we're going to plug both of those equations, or put both of these equations to the above ones. We'll take r squared and we're going to plug it in right here. And we'll take dQ and we're going to plug it in right there. So if we do that, we then have an equation that tells me the electric field magnitude due to that differential charge element is equal to K times lambda divided by z squared plus capital R squared multiplied by ds. Step 6, well, that's only the electric field for a single differential charge element. If we want the electric field at point P due to the entire ring, we're going to have to put all of our differential charge elements together. Now, as we identified back from the first step, the only part of the electric field that matters is the Z component, because when you put all the differential charge elements together, at the end of the day, all the X and the Y components are going to cancel off. So what I really just want to know is, what is the Z component of the vector dE? And that's what I've said here. We only need to figure out what the magnitude of the electric field at point P is due to the differential charge element dq in the z direction. So I just want dEz. So again, to help out with the geometry, we'll just look at this picture from a top view perspective. So again, like, because that dE vector, again, is a three-dimensional vector. It has both an x, y, and it has a z component to it. So from a top view perspective, okay, we have this picture. And again, if you look at this, the differential charge element has a charge that is, it's a positive linear charge density. So it's positive, which means if you put a positive test charge at point P, that positive test charge is just going to repel away from this line that connects point P to dQ. I'm going to identify another variable, or I don't think you call it a variable right here, but yeah, I guess technically it would be a variable for like all the differential charge elements, but we have phi. So I'm going to let phi represent the angle between the length z and little r. So in the picture, that would be for my right angle triangle, this would be this angle that's bound down here between z and r. Now, if we draw from a top view perspective, what the electric field is at point P due to dQ, it'd be a vector that points down and towards the left. Now, just be aware this vector actually does point into the page as well because it does have a y component to it, but we don't really need to worry about that to properly calculate what exactly the z component is going to look like. So if we look at this picture, we're going to identify dEz. That's the z component of that vector. That's going to point down or towards the bottom of the page from our perspective. And then dEx is going to be a vector that points towards the left. And if we look at the geometry, we just want to take this angle phi, and we want to identify which angle in this triangle is going to match up with. And then it does match up with this angle. And again, you can do some simple geometry with angles to figure out what phi is, but those two angles do match up. Therefore, if we know what dE is, and we have an equation from that on one of the previous slides, the z component dEz, well, we're going to make use of the hypotenuse of the triangle, which is dE, and we want to calculate the adjacent side. Therefore, dEz is going to be equal to dE times cosine of phi. Now, we know a couple things here. So first of all, dE is equal to k times lambda divided by z squared plus capital R squared, and we multiply that by ds. I also want to know what is cosine of phi. Now, to figure out what cosine of phi is, I can look at, so we use this triangle to identify what the z component is in terms of phi. We're going to use this triangle at the very top to identify what cosine of phi is based on these different lengths. So using this top triangle, if we look at cosine of phi, that would be equal to side adjacent over side hypotenuse. Side adjacent is z, and then side hypotenuse is little r. So therefore, we have cosine of phi would be equal to little z over little r. Now remember, in a previous slide, we have an equation for what little r is. So little r is equal to the square root of z squared plus capital R squared. And now we're just going to take these two and we're going to sub it into the equation up here. So dE goes in the place of here, and then cosine of phi, we're going to put in the position there. So what that'll give me is you have the z component of the electric field due to that differential charge element is equal to k times lambda over z squared plus capital R squared times ds. And then multiply that by z divided by the square root of z squared plus r squared. In terms of simplifying this, the denominator, you can write down z squared plus r squared as being to the power of 1. So we have a couple of common factors we can combine here. So this would be z squared plus capital R squared to the power of 1. This square root would be z squared plus r squared to the power of 1/2. So if you combine those common bases together, you just add the exponent. So this would be an exponent 1. This would be exponent of 1/2. 1 plus 1/2 would be equal to 3/2. Therefore, we have an equation that tells us that the magnitude of the electric field at point P due to that single differential charge element is K times lambda times Z divided by Z squared plus R, capital R squared, all to the power of 3 over 2 multiplied by ds. But again, we still have not identified what the total electric field is. So now what we're going to do is we're going to put all of the differential charge elements together. And the way we do that is we're just going to take this equation, the DEZ equation, and we're going to integrate it over the entire circumference of the ring of charge. So setting up my integral, on the left-hand side, we're going to integrate from 0 to E, which is my total electric field of DEZ. And on the right-hand side, we're going to integrate. So again, just notice my variable in which we're integrating with respect to is ds. So that's how we're going to set up our limits of integration. And we're going to integrate that from basically starting with having no differential charge elements to considering all of them over the entire circumference of the ring. Now, when you look at this, so this side of the equation is just going to simplify to being the total electric field. This side of the equation, before we integrate, we want to pull out anything that's constant. Now, the nice thing about this is when you look at this equation, almost everything is constant, actually. So K is Coulomb's constant, lambda is the linear charge density, Z is just some kind of fixed position away from like the center of the ring, and then capital R is the radius of the ring. So all of this can be pulled out of the integral. So that's going to give you your electric field is equal to K times lambda times Z divided by Z squared plus capital R squared, all to the power of 3 halves. And then we're going to integrate from 0 to S ds. Now, if you want, you can actually figure out this antiderivative. Technically, you just have 1 ds there, in which case the antiderivative of 1 with respect to ds would be s. Or you can just physically understand like what this means. So what this means is you take the ring of charge and you break it into a bunch of ridiculously tiny sections of the ring in terms of arc length, and the integral says put them all back together over the entire circumference of the ring. So if you take the entire circumference, break into a bunch of different pieces, and then put them all back together, that is just the circumference of the ring. And the circumference of the ring is equal to 2 pi times its radius, and its radius being capital R. Therefore, we have an electric field equation that would be equal to K lambda Z divided by little z squared plus R squared, capital R squared that is, to the power of 3 over 2, multiplied by 2 pi times capital R. Okay, we can simplify just a little bit here. So we have E is, I don't should say simplify as much as this combines. We have E is equal to 2 pi times capital R multiplied by K lambda Z over Z squared plus capital R squared to the power of 3 halves. But just one thing to consider here. Yes, the linear charge density is lambda, but that's also equal to the total charge in the ring divided by its circumference. Circumference of the ring is 2 times pi times r. So I'm just going to substitute this equation, so for lambda in here, and it'll just simplify the equation a little bit more. So if we plug it in, we would then have 2 pi times capital R times K times Z. Okay, and then in brackets here, the lambda is just being replaced with this expression, which is capital Q over 2 pi times R. So the only reason I did this is because there's just a few things that cancel off now. The 2's cancel off, the pi's cancel off, the capital R's cancel off, and then it tells you that the electric field magnitude, we know the direction is towards the right here, but the electric field magnitude from the center of a ring of charge and by a distance z is equal to K times Z times capital Q divided by little z squared plus capital R squared, all to the power of 3 halves. And that's it for this lesson. So in your assignment booklet, complete the questions in the section on the electric field on the axis of a thin ring of charge. And then in the next lesson, we'll look at what's going on in terms of electric potential due to a continuous charge distribution. And I'll talk to you then.